So hello. So first of all, thank you very much for the organizers for inviting me such a nice, place, much nicer than Stuttgart. I'm sorry. And besides, it's great to see, kind of all the new friends, here. And although I'm, from field of inorganic, but physics is quite, common. And so far, I really enjoyed the lively discussion here. So today, somehow, organizer kindly give me 15 minutes with the pressure of, providing a general introduction of quantum spin liquid. But I realized many quantum spin liquid talks in this conference, already. So you might feel a bit tired, but, it's kind of too late. And, let me begin with a general introduction of, quantum spin liquid. Then I would like to speak about two topics related to Kitaev quantum spin liquid. One is iridate. The other is nowadays quite star in Kitaev community, ruthenium chloride business. And if we have time, I want to briefly mention about Kagome, but I don't think I have time. And so this work was done in collaboration with those people listed here. In particular, Jan Bruin, Ralph Klaus, and Yosuke Matsumoto Stuttgart. They are kind of key player of our project in Kitaev physics, and those are kind of difference. So, sorry for this undergraduate introduction, but the conventional magnet, okay, with lowering temperature. You have kind of broken symmetry below total temperature, and the spin entropy should be rapidly quenched. But in a quantum spin liquid, no magnetic ordering, no symmetry breaking down to T equals 0, and it remains, quantum disordered. And the spin entropy should be quenched only gradually, but down to 0 because of some dynamic law. And that's experimental version of the definition of quantum spin liquid. And why quantum spin liquid is so interesting? Of course, quantum spin liquid is believed to be a quite entangled state, quantum entanglement. And you see, exotic QSL particle excitation. That's kind of hallmark of a quantum spin liquid. And we are supposed to see fractionalization of spins. And we are supposed to see like spinons, Majorana fermions, upon what kind of quantum spin liquid that you are working on. And in particular, in this organic community, connection to superconductivity has been discussed in some sort of spin pair to Cooper pair. And since we are searching for system without any kind of ordering, in some sense, our playground is something like along Japanese Zen concept, and the central dogma of Japanese Zen is go to state of nothingness, okay, like Zen garden. But okay, there is a kind of topological pattern, in this, garden. And if you go state of nothingness, you see hidden reality. That's kind of a central dogma. And of course, quantum spin liquid seemingly nothing, but underneath you have, quite, exotic excitation hidden. That's kind of hidden reality in quantum spin liquid business. And that's why, Japanese, like quantum spin liquid very much. Okay. And this, quantum spin liquid business, I think as far as I understand, kicked off by, 1D Heisenberg antiferromagnet, starting from, Bethe ansatz, even before Second World War. And somehow after that, ground state energy was calculated, and the excitation was kind of understood, in kind of 60s. But then 70s, Phil Anderson proposed, quantum spin liquid, could be realized even higher dimension, in particular 2D, like a triangular lattice. And that kicked off, a kind of exploration of a quantum spin liquid, over a wide range of compounds, including triangular lattice, Kagome lattice, Pyrocola lattice. And it was kind of, at the heart of, quantum magnetism for long. Recently, Alexei Kitaev proposed elegant and beautiful model on honeycomb lattice. And unlike, 2D, this, Kitaev model is kind of exactly solvable. And that attracted a lot of, attention. And many, people are now heading towards a realization of Kitaev quantum stability. And that's kind of my kind of main topics. But before, going into Kitaev topics, using a first, 15 minutes, let me go through, from 1D Heisenberg antiferromagnet to Kitaev. Okay. So there was a, kind of a specialist discussion, okay, by Kelly, last night. So it's a shame to show something like this, but this is a experimentalist image of, quantum spin liquid in 1D, RVB-based. So you have, different distribution of a singlet, bond, and you have, many different way of distributing a singlet, bond, short range, long range, and it's kind of quantum superposition of those states. So quantum mechanically disordered state. And the hallmark of, quantum spin liquid in 1D is fractionalization of spins into spinons. And as, Terry, mentioned last night, spin one excitation, the flipping spin, could split into spin one half. And once, they split, in the Ising model, you can, move spin one half, domain world without, costing any energy. And going to, XY, because of this, S plus, S minus, S minus, S plus, term, this acts like a hopping term. And in case of XY, so you have a fully spinon band, okay, and forming a spinon kind of Fermi surface. And in case of Heisenberg, those, as a term, give like to kind of interaction term, and you have, somehow C of spinons with, interaction in case of Heisenberg, 1D, magnet. And experimentally, okay, and if you have, C of spinon and the excitation like, metal, and you are supposed to see continuum of excitation, and that's kind of a signature of fractionalization of spins. And in the experiment, like a neutron, inelastic, X-ray scattering, so you can see a continuum of excitation beautifully in 1D Heisenberg magnet. And besides, if you take a look at susceptibility, you have, finite susceptibility like a Pauli susceptibility at low temperature. And you have, almost, linear specific heat at low temperature. And they are kind of scaled by 1/J. And also their ratio satisfies, Wilson ratio. Wilson ratio is close to 1 for those, compounds. So it looks like, electrons in metals. And in 72, shortly after establishing those, excitation in 1D antiferromagnet, Phil Anderson proposed that, even in 2D, you can have, quantum spin liquid. And if you take a look at, his seminal, apparently he was, motivated by the discovery of dimerized state in vanadium oxide. Okay, there are many, vanadium B1 oxide which, dimerize into singlet state at low temperature. And he thought perhaps, spin singlet state is, much more stable than one might, think. And I think that's why he hit the idea. And if you have, triangular lattice, of course, as many of you know, you cannot, satisfy all the bond, and two happy and one unhappy bond. Okay, so therefore, if it is antiferromagnetic, you can gain only 1/3 of, antiferro coupling energy because of a frustration. And if you calculate the energy for antiferro state and the singlet state, because singlet state, okay, for one bond has, lower energy than antiferro state. So that therefore, singlet, state, could be stable at the end of the day. That was kind of his point. And nowadays, people understand, the ground state of RVB-type quantum spin liquid is a kind of superposition of, state with, different, spatial distribution of a singlet, pair. And you can have, more than one kind of quantum spin liquid, like a superposition of only, short length, singlet, pairs, where, you are supposed to see excitation gap. On the other hand, you can have, superposition of, singlet, which kind of short range, long range, whatever. And that is called the long range RVB. And in this case, because of the presence of a long range, singlet, you are supposed to have a gapless, excitation. And in reality, of course, it is kind of well known. In case of, triangular lattice, if you have only nearest neighbor interaction, the ground state should be 120-degree order. And in order to stabilize, those states, some additional ingredient, is kind of required. For example, close proximity to metal to insulator transition, Anton discussed, this morning. But he said it's not in RVB, but maybe, likely chiral or spin liquid, around the metal to insulator transition. And of course, if you go, Kagome, from, triangular lattice, because, you have only, 4 neighbors, okay? And that stabilizes quantum spin liquid. And without doing anything only with the nearest neighbor, people believe, quantum spin liquid state should be realized in Kagome. However, because, we don't know, exact, ground state, and there is kind of a ongoing discussion over decades whether the ground state is a gapless, this type of a spin liquid or gap Fujitsu, spin liquid. Still, we don't know the answer. And of course, those 2D quantum spin liquid, if you have long range RVB, again, spinman excitation is believed to split into, 2 free, fermions, spinon excitation, and they form, Fermi surface of neutral QSI particles. And of course, if you can measure, excitation spectrum, because of this C of spinons, you are supposed to see continuum excitation. Okay, in contrast to we'll define the magnon dispersion. And somehow, motivated, by this, material people try to look for kind of compounds with, triangular motif over decades, and at least, I should say we, but maybe we kind of discovered many triangular-based compounds, including triangular lattice, Kagome lattice, which doesn't show signature of magnetic ordering down to the lowest temperature measured. Maybe say 1%, 0.1% of exchange coupling, J. Okay, and of course this is kind of a first signature. We identify nothingness, one of the central dogma of Zen. But of course, in order to establish quantum spin liquid, perhaps we should capture fractionalization speeds experimentally. But unfortunately, although there are many compounds which doesn't show long range ordering, but it's quite hard to capture such signature. And as far as I understand, I was jealous to this organic community. I thought organic is kind of closest to capture signature of fractionalization. And in fact, this compound, the MIT, organics, Kato-san discovered. Okay, so first of all, you don't see any signature of long range ordering down to 20 milli-K, like a BD salt. And you see T linear specific, like metal, and Pauli like susceptibility, and they satisfy, Wilson ratio close to 1, like Fermi liquid. And I think this compound I believe that finally, they captured the, spinon Fermi surface because of, seminal work, by Matsuda-san. So he measured the thermal conductivity down to low temperature. And you see, thermal conductivity divided by T as, finite intercept. And since, thermal conductivity is product of heat capacity, so T linear term times, mean free path, right? So, and they observed quite, large, thermal conductivity comparable to metal, like, brass. And they concluded, mean free path, could be micron. It was a big surprise. And it was taken as, the presence of highly mobile excitations. Okay? And I thought it's definite evidence. But somehow, recently, some question arises, about the reproducibility of this result. And I understand, recent, work Yamashita said it depends on a kind of a cooling rate. And if you cool down material, very slowly, you start seeing this linear thermal conductivity. But according to Kanoda-san, it's not, confirmed yet. So the situation is quite, chaotic. And I heard, many stories about BDT in this, meeting. And BDT could be even chaotic. There is a mysterious state transition. And the ground state, might be gapped and look like random singlet. So in that sense, it's quite interesting, but not yet, established yet. And in organics, we can have, so-called Kagome model system called Herbertsmithite. And some time ago, Yong-san Lee did Newton, inelastic scattering measurement, and he observed a beautiful, continuum, scattering in the neutron, scattering. And he claimed, okay, it's kind of a signature of a fractionalization. Okay? And I think this result is still kind of robust. But nevertheless, then people try to ask, whether, Kagome has, gap or gapless or U1 or G2, they ask. But somehow, still, there is a conflict NMO, conflicting two NMO kind of results. One said, okay, night shift decays like exponentially, so there should be a small gap. But the other said, okay, night shift, decreases linear in T, so therefore it's like a Dirac and, somehow it should be gapless U1 quantum spin liquid. And this confusion hasn't been solved yet. So many, experimental question marks, still, in a 2D, quantum spin liquid. Yes. Yes. Yeah. So in particular, this Herbertsmithite case, there is kind of exchange of zinc and the copper, but that happens between layers. That's kind of their logic. The system could be relatively clean, but nevertheless, you cannot ignore the presence of a magnetic copper in between Kagome layers. And the claim of NMO people is okay. We measured the night shift, for the copper away from this impurity.
And there, you think results to kind of indicate that some students also by
Yeah. So this one said gap, but more recent one from OSE, they say gapless. It's
more recent one.
Distribution of that's a kind of they say it's kind of mixture of this and this. That this one said yes. And of course even 2D RVB, it's quite confusing. But somehow recently fresh fuel came from Kitaev. And maybe this, Kitaev quantum spin liquid might be easier to identify experimentally because of a topological state. That's why, people rushing to that business. And I think some time ago, almost 15 years ago, Kitaev, published these, papers. And he kind of proposed the, quite, simple, but elegant, model on honeycomb lattice. Okay? So he placed the spin 1/2 moment on top of honeycomb lattice. And he connected, those kind of spins, okay, by ferromagnetic Ising bond, okay. And there are 320 bond, and one is, within Ising axis, along X. So that's, this bond try to polarize spins in X direction. And this one is Y bond, so try to polarize spins for Y direction. And this one, try to polarize the spins for G direction. And the XYZ kind of orthogonal to each other. So therefore, this spin, doesn't know, which, bond, he should obey. So that's kind of a source of frustration arising from conflict of, 3 bonds. And that's why, we have, quantum spin leaking. And I think, experimental way of, understanding this, for example, you might, consider like you can choose one bond and distribute the ferromagnetic, pair of bond, spatially, and then you can consider, quantum superposition of different distribution of ferromagnetic, bond, like RVB. Okay, so that's kind of our kind of naive picture. But what is great about this Kitaev model is unlike in RVB, we don't have to rely on this kind of cartoon picture. But by introducing Majorana operator for spins, okay, so you just express spin with 2 kind of Majorana operator, one B, okay, and the other kind of a C operator. And the B kind of it's called the local Majorana, representing those kind of bond, okay, and they are kind of forming a loop, called the G2 Hill flux, and this flux component should be uniform in the ground state, okay, and actually Hamiltonian can be written like this way, and this factor Uij is made of those localized Majorana. And once it becomes uniform, okay, this is kind of constant, right? And as a result, the only this C operator remains in a J form tight binding in honeycomb band. That's why in the ground state you have Dirac dispersion of C Majorana fermion. And we have C of Majorana fermion in the ground state. And at this stage, the ground state is kind of gapless. So it's not, fully topological yet. But once, you apply magnetic field, okay, so you have, excitation gap, at, Dirac, point. And now, the system can topological. And this, gap, okay, in the Dirac cone emerges as, topologically protected edge state. Okay, so you have edge state arising, Majorana fermions, and this in edge state because they are neutral particles, so you cannot measure electrical resistance, but you can measure thermal Hall effect, like quantum Hall effect, and Kitaev specifically predicted under magnetic field, you are supposed to see quantization of thermal Hall effect with this quantized number. And there is a factor 1/2. This 1/2 come from we have 2 kind of Majoranas, C and B. That's why we have half here. And therefore, unlike spinons, we have quite stable topologically kind of protected edge state, hopefully, and this could be a definite signature of quantum spin liquid state. I think that's kind of advantage of Kitaev quantum spin liquid against RVB type quantum spin liquid. And of course, we have to develop material which mimics essence of a Kitaev model. And soon after Kitaev model was proposed, my Stuttgart colleague Georgi Jackeli and the Guignard Kavulin proposed a kind of a strategy to realize Kitaev model in existing compound. And they proposed, okay, since spinon half, okay, exchange coupling is normally Heisenberg, right? So instead of using a pure spinon half, why don't we use spin orbital coupled moment, pseudo spin J1 half? And since J1 half is a kind of a composite of spin moment and orbital moment, and the orbital moment could be anisotropic and give rise to Ising interaction. That's their idea. And they kind of propose if you place like a D5 compound, like iridium 4 plus, ruthenium 3 plus in octahedral case, like a perovskite, right? Then you have T2G5 configuration, one hole in T2G band, and following LS coupling regime, so you have L equal 1 and S equal 1 half. And if you have less than half field, okay, you are supposed to have an opposite sign of L and S, right? So therefore L minus S equal 1 half, and so you have spin 1 half like J moment here. But of course, major component of this is kind of orbital. You can see L equal 1 contribution, and this gives rise to kind of quite big anisotropy. And at the end of the day, regular exchange process is kind of prohibited due to this phase factor I here due to interference of two oxygen in between, and because of those L moment, the interaction is failure and quite Ising. So if you kind of place two octahedron by sharing edge, so you can have Ising ferromagnetic coupling here, and this is basis for Kitaev model. Okay, and as you see, like octahedron has three orthogonal edges. If you imagine octahedron, and so using those kind of three orthogonal edge, so you have kind of a bond, okay, with perpendicular to X, Y, G, perpendicular to each other. So Ising axis is kind of perpendicular to each other. So that's an essential ingredient of Kitaev model. And now once you have this, we have some sort of Lego blocks, and using those 120-degree bond, it's quite easy to form a honeycomb lattice by sharing edge, right? And solid state chemists note, this kind of edge shared network of honeycomb is quite popular. And there are actually a number of compounds which takes this kind of geometry with honeycomb lattice of iridium 06 or ruthenium chromium 6 octahedron, like lithium iridate, okay, which has honeycomb network plus lithium in between honeycomb layers. And this was discovered for the sake of battery research. And sodium iridate, similar material, or ruthenium chloride, without any lithium sodium there, only honeycomb network. And everybody, including our group, rushed into those compound and measured the properties. But as you see from this figure, you can see clear specific anomaly at low temperature. And all compound proposed in early days shows long range magnetic ordering, either zigzag or spinon. Okay, so in the sense that no quantum spin liquid at the beginning. So we faced difficulty in approaching quantum spin liquid 10 years ago. But recently, I think we got some progress along this direction, and in particular, let me say two new arenas kind of developed. One is hydrogen honeycomb we discovered, and the other is star compound ruthenium chloride under magnetic field. Now, So this is compound we discovered some time ago, and since lithium iridate didn't work, we used yes some chemistry, and there is a lithium in between the honeycomb layers, and we kind of simply replaced this lithium with proton hydrogen using electrochemistry technique, battery technique. And somehow replacement of lithium with hydrogen, changed property of this honeycomb compound a lot. And now susceptibility like this, and we don't see any kind of a signature of ordering. And like organics, we did the NMR for both lithium and hydrogen, and down to 1K or recently down to 15K. We don't see any signature of broadening of NMR peak. So at least nothingness is kind of achieved here, and we claim the quantum liquid ground state achieved in this compound. Finally, in honeycomb-based compound. But then we went to explore signature of Majorana fermions. That was of course our biggest task. And first we measured specific heat, but somehow specific heat was kind of boring TQ. And according to numerical calculation, because we have this flux gap, very small flux gap, and this 50% of entropy associated with the flux remains down to low temperature, and we are supposed to see huge entropy at low temperature, something like below 1K, below 2K, but unfortunately we didn't see anything, and it's like somehow the system has excitation gap rather than accumulating a lot of entropy at low temperature. And more recently, we kind of replaced hydrogen with deuteron, and we did the kind of isotopic experiment. And somehow we are a bit surprised. Just replacing hydrogen with the deuteron, susceptibility changed a lot, and Q device temperature was doubled, from 100K to 200K. So it's kind of huge change. And we believe now, it is, due to, this exchange coupling is through kind of oxygen, and the covalent, bond with the hydrogen, changed the, iridium oxygen hybridization a lot. That's why. So it's kind of a signature of super exchange kind of important in this system. But according to kind of a theory, you find phase space, as a function of magnetic coupling. Only narrow region, Kitaev quantum spin liquid could be stabilized. But like with change of factor of 2 in magnetic coupling, still we do see a quantum spin liquid state. Somehow our quantum spin liquid kind of too robust against perturbation. And from those, somehow I think the physics of quantum spin liquid state in this compound is quite interesting, but this system may not be ideal system to search for Kitaev signature. That's somehow our conclusion. Yes. No.
Because you say that it is boring, that what it is only formulas. Are you sure there is no entropy?
Yeah, of course, there is no label, but seemingly, yeah. And also, yeah, Colin Broholm, he did the neutron scattering research, not all published yet, but there seems to be a kind of gap in excitation. So, gap is something like 10K. Yeah. So there might be something, but yeah. Roughly 100K. Yeah. So, but because of that, we suspect maybe some sort of a random single state like a DDT, might be happening here. So we are suffering, same issues, as organics. And in parallel with the dots, new, class of compound start emerging. And now I think it's a kind of star compound. I'm a bit jealous about this. The ruthenium chloride. Perhaps you might have heard about this compound, here and there. And that's, again, a honeycomb, compound, edge shared network of ruthenium chlorine octahedron. And this compound at, 7.5 K ordered antiferromagnetically. And you have, zigzag type, ordering at low temperature. So in that sense, in the zero field, it's not, quantum spin liquid, magnetically ordered state. But people, applied magnetic field. In particular, if you apply magnetic field parallel to honeycomb plane, you suppress, magnetic ordering at 7.5 K, and goes on, and eventually magnetic ordering goes away. But in system, doesn't show saturation yet. We have only 0.6 μB moment here, and somehow people start recognizing, this state might be able to be viewed as field-induced quantum spin liquid state.
So the excitation of the 3D system, this is again the Majorana with the Lilr₂O, or what do you expect from the heat profile?
So yeah, so there are actually two kind of characteristic temperature. Okay, and there are two kind of Majorana. And at high temperature, somehow correlation starts happening. You quench 50% entropy, and there is this flux gap, and that gap is supposed to be very small. Like
so you think you're above that?
Yeah.
Ah, okay.
Yeah, and so therefore, with lower temperature, if it is kind of pure KF, we see a kind of huge peak in specific heat coming from flux component.
But below that gap, I would expect.
Yeah.
But you say
Yeah.
you don't see the gap.
Yeah, but if I do believe like a numerical calculation, this gap is with the order of 1K, and if it is kind of anisotropic, even kind of smaller. So therefore, if there were kind of signature of 50% entropy kind of hidden, yeah, we believe we should see that. And somehow, in this field-induced state, people observed some strange signature here and there. And first of all, a group of Oakley, they kind of discovered the continuum excitation in inelastic neutron scattering, and they claimed, okay, this is some signature of fractionalization. Then, the group of Yoji Matsuda, Kyoto, they measured thermal conductivity following prediction of Kitaev. And right after the collapse of antiferromagnetic phase, they observed, relatively large, thermal Hall effect, and this is, half quantization value, and somehow there seems to be some sort of, plateau state, okay, within half. Yeah. Yeah, that I'm going to speak. Yeah, and actually, yeah, I gave a question, yeah, as a functional field, this is original data by Matsuda-san, and this looks like quite plateau. But if you take a look at, say, temperature dependent, right? So they say, okay, this is kind of plateau, but in reality, this is kind of expansion of this part, and I cannot deny, this goes down, rapidly toward this direction. So in that sense, whether it is kind of plateau or not, it's not 100% clear. And in parallel with that, the group of Pan Ong at Princeton, they kind of reported something which could be even kind of more exotic. So okay, so this is longitudinal thermal conductivity. Okay, not thermal Hall. This is just thermal conductivity. Okay, in other functional magnetic field, you see a lot of oscillative feature. And they said, okay, this is, quantum oscillation and plotting 1/h, there is some periodicity. And they deduced a kind of small Fermi surface out of that. And so there should be underlying hidden Fermi surface of a neutral particle. That's what they did. And they measured thermal hole as well, but they say they didn't reproduce Matsuda result. So there is just kind of broad peak and no kind of plateau. That yes.
Yeah, I have a question about because in Matsuda's presentation, how explain what binary multiplied by length scale? Because she talked about if it is 80 feet of the edge, you have no meter. In this data, there is a length scale. So my question is, because there is a plateau here, if you want to find the plateau, but is the number similar?
Yeah.
So
yeah, of course, yeah. And so normally actually we normalize per layer instead of absolute value of kappa xy. Yeah.
So how does that neutral particle couple with the magnetic field?
Even this one.
You have a neutral particle there, right?
Yeah. I don't know. That ask Pang. Okay.
Very good.
Yeah. Okay, but yeah, but my story is I don't believe it is a quantum oscillation. Okay. So that's kind of unfortunate. Yeah. So in the situation again a bit chaotic, like organic community, and I was a bit jealous about lithium chloride, and I didn't want to touch it, but somehow I couldn't stop my young people started working on that, and I asked what can we do, but anyway, so it might be important to confirm whether half quantization is there or not, and see oscillative structure and confirm ongoing claim that could be kind of important. And fortunately, we got I think. Okay, I have to finish in 5 minutes. Yeah. So fortunately, Yuji Matsuda, yeah, he's a good friend, and he allowed me to access same crystal. And also we have CVT crystal that's kind of similar to Princeton crystal from Vecina group of Vecina. So we have two different class of material. One is close to Matsuda, and one is close to On. And so this is a kind of picture of those two different crystals. And I believe or not, their crystal structure at room temperature different. So they are so different. And we reproduced kappa XX. This is total result, and this is our result. And you see, kappa XX the same. Right? And this is somehow magnetic field dependent of kappa XX, longitudinal thermal conductivity. And you see again, quite complex structures here and there, right? But actually immediately you notice a very sharp structure around 6 Tesla and 7.5 Tesla. But this is exactly at the phase boundary of the collapse of a magnetic order. There are kind of two critical points. Okay, there's the phase 1 and phase 2, and those exactly coincide with magnetic phase transition. And of course, at the magnetic phase transition, you have a soft magnetic excitation that scattered kind of phonon, right? So those deep can be understood as phase transition. And there are additional features here and there, and we thought there could be a hidden transition here and there above. But of course, you might ask me how about quantum oscillation? Okay, and somehow we investigated a lot, and our conclusion is it's highly likely additional phase transition at high field and low field rather than quantum oscillation. And let me, yeah. So our reason is the following. First of all, okay, so this is a comparison of thermal conductivity, and this is data from Princeton, and you see deep and peak, around the same magnetic field. So because we are taking a look at same phenomenon, okay. But like our sample apparently has higher thermal conductivity. That means somehow our sample is a bit cleaner than the others, right? But nevertheless, you see this oscillative structure kind of smaller. And of course, in a classical quantum oscillation, the cleaner amplitude, large, right? So it's kind of opposite. And second, like in a quantum oscillation with lower temperature, amplitude should, grow towards, t equal 0. But somehow below 1K, we find that this, amplitude of oscillation start decreasing. Right? So that's again, doesn't follow, quantum oscillation scenario. And also say like, we see quite big, temperature dependence of deep and peak, position. And, those kind of magnetic phase boundary because of entropy effect. You see a kind of big tilting of phase boundary, and it really look like phase, boundary rather than quantum oscillation, which should have constant peak temperature. And of course, you may ask me, what it is, and at least we found, unfortunately, this high temperature features are kind of smoothly connected to tiny anomaly around 30 Kelvin, which is called the 14K or 13K phase, which likely comes from kind of infinity phase, okay, due to stacking disorder. And the high temperature feature, we don't know what it is. And the group of Matsuda claims, this is nothing but a topological phase transition. But I have some question mark, on that. And finally, the thermal Hall effect. Okay, so this is kind of thermal Hall effect, and this is kind of a phase, boundary, and you can see sizably big, thermal Hall effect. This dotted line is calculated half quantization value. So number of layers are calculated. Okay, and somehow at the located below 10 Tesla, somehow there is some flat region, but it just smoothly goes down. Okay, so you don't see any kind of plateau. But at higher field, although the resolution bad, but somehow kappa XY stays rather kind of constant around the half quantization bar. And this is so-called field sweep. We sweep in magnetic field, okay, at fixed temperature. And to check, our experiment, we did the temperature scan. At the fixed field, we scan temperature, and those two data agree with each other. And this is kappa XY as a function temperature, and you can see below 10 Tesla, it's kind of smooth and nothing special at the half quantization value. But if you go higher field, something starts, happening. Okay, and there seems to be some kink and some plateau seems to be developing, like that way. Of course, within the solution. Okay, that's kind of our bet. Yeah. The first data, but the second data shift to 10 Tesla.
So now the state, just to be sure, I understand that kappa is the experimental observation, the kappa is field independent, for example, and temperature independent, the final medium.
Yeah. So like this is kind of my last slides. Okay. So so this is kind of a color plot of our thermal Hall effect, and white is half quantization value. I'm sorry, plus minus 15%. Okay, not plus minus 1%. Okay, but somehow, so this is around the half quantization value, and as you said, at high field, this whole region tend to kind of spread, right? So in that sense, it's not inconsistent with Matsuda report, and of course at low field, somehow thermal Hall effect tend to be suppressed.
So you have one factor, then another factor,
You mean this one?
What stops at 90?
It's a kind of technical reason. What I recently feature, it's hard to go up. Yeah. Yeah. But anyway, so they're kind of suppression, and you see some kind of streak coming out, and this is nothing but it's a dip of KXX, and I associate to some sort of a magnetic phase transition, and somehow, yeah, I don't understand why. But those magnetic phase transition tend to suppress kappa XY, and I think that's kind of a kind of source of a discrepancy between Matsuda data and our data. But anyway, so what we can say at best is within our resolution, consistent with Majorana edge state scenario. But since our resolution is plus minus 50% as a scenario. Like some people emphasize, okay, it can be just Magnon summer holiday, or recently island from Cameron, Honon could kind of contribute. So in that sense, those cannot be excluded. Yeah.
Do the experiment again. Is there any dependence on the size of the sample?
That's good question, and so far it's kind of time-consuming experiment, and we go through kind of a 3 sample with a different geometry, and among those 3 from the same batch, the result was quite reproducible, and the size was different.
Say it's an edge state, obviously.
Yeah. Yeah, yeah.
Because I thought if the quantum of scenario is 2, this is all edge.
Yeah, yeah.
If you make a hole inside the center, you should have a black percent of X down and X is the different.
Yeah.
Let's assume that we agree with this scenario, with this idea of extremely disputable. We accept that this is in state of state of this arrow. You have to couple that to points and you have to follow points. So therefore, you are not really expecting the same type of quantum point effect as you have in electrical electrons, charges. So it's a little bit different. So here we are coupling to the phonons, then it's going to see something like that. However, the question is.
No. Yeah. I got same comment from Concretin in the check, spatial distribution. Yeah. No. I think I'm done. Yeah. So yeah.